In this video, we will do another linearization example. So let's let f of x comma y be equal to the square root of x squared plus y to the third. And in part A, let's find the linearization to f at the point 6 comma 4. So I'd like you to pause the video and try this on your own first. If you need to review the formula for linearization from the previous video, definitely go ahead and do that. But pause the video for about 2 minutes to try this question on your own first. So 4, 3, 2, 1, pause the video. Pause it for 2 minutes to try this question first. Alright, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to try this. So let's talk about it together. So if I want the linearization, I'm going to need to find some partial derivatives and plug in this known point 6 comma 4 into it. Alright, so I'm going to need my x partial derivative and my y partial derivative. So taking the derivative of this with respect to x first, I can rewrite this square root as a 1/2 power. This is x squared plus y cubed to the 1/2 power. And now taking the x partial derivative, the 1/2 comes down. I get that whole thing to the negative 1/2 power. Keep the inside the same, x squared plus y cubed. But now I do chain rule, I multiply by the derivative of the inside with respect to x, which is 2x. Alright, and now let's plug in our known point. So my x partial derivative evaluated at 6 comma 4. I notice that the 2's are going to cancel. And then after that, when I plug in 6 comma 4, what we'll end up with is 6 will get plugged in for the x, and that'll be in the numerator. And then on the denominator, when I bring the negative 1/2 down, it'll become a positive 1/2 power, which will become a square root in the denominator. And if you plug in 6, we'll get 6 squared, which is 36. If you plug in 4 for the y, you'll get 4 cubed, which is 64. So we'll get 64 plus 36, which is 100. We'll get 100 within the square root. So this is 6 over 10, which becomes 3 over 5. So now let's do the y partial derivative. So the y partial derivative is going to be 1/2 times x squared plus y cubed to the negative 1/2 times the y partial of the inside. That's using the chain rule. So that's 3y squared. And now let's plug in. So we get the y partial evaluated at 6 comma 4. And doing this one, I'm going to do this one more quickly. We'll end up with 24 over root 100. And this simplifies to 12 over 5. Okay, so we have our partial derivatives. At this point, we are ready to write down our linearization, or sometimes we call this linear approximation. So the linearization, I'm going to call this L of x comma y. It's a function of 2 variables. We start off by writing the value of the function at that point. So the very first thing that we would need to write is we would need to write what is f of 6 comma 4. If you plug 6 comma 4 into this function, you'll get a square root of 100, which is 10. And then plus, now we do the x partial derivative, 3 over 5, times x minus the known x coordinate, which is 6. And then plus the y partial derivative, which is 12 over 5, times the change in y, which is y minus the known y coordinate, is 4. Okay, and that is our linearization right there. The reason we use this is approximately equal to our function, square root of x squared plus y cubed, near the point 6 comma 4. It is a really good approximation for that, near the point 6 comma 4. Okay, so I'm going to box this. Okay. The advantage of having this approximation, as opposed to just the original function, is the approximation is easier to evaluate. Especially if I had to do something like this without a calculator, it is way harder to plug in numbers into this square root function than it would be to just plug into this linear function that I've obtained now. All right, let's do part B. Now let's find the equation of the tangent plane to the equation z equals f of x comma y. So if we think of this function as being some surface, let's find the equation of the tangent plane to it at the point 6 comma 4 comma And 10 is what you'd get if you plugged in 6 and 4 for the x and the y respectively. So 10 would be my z coordinate. So the key idea there is we've actually done all the work. The tangent plane is z equals L of x comma y. What I mean by that is take this formula that we just got for the linearization and set it equal to z. And that's my tangent plane. This is the equation of the tangent plane in general. Okay, so all I have to do is just change L of x comma y to z. And we get z equals 10 plus 3/5 x minus 6 plus 12/5 times y minus 4. And that's the equation of our tangent plane. All right, so now let's actually use this to do an approximation. Part C, let's approximate square root of 5.9 squared plus 4.05 cubed. So it looks like our function, but where we plug in, x is now 5.9, and y is 4.05. So let's plug these values in into our linear approximation, into our linearization. That's just another word for linear approximation. All right, so doing that, we'll get 5.9 squared plus 4.05 cubed square rooted. So our expression is approximately, let's write that better, approximately going to be equal to, let's take our tangent plane equation, 10 plus 3/5 parentheses plus 12/5 parentheses, and this one has a minus 4 and the other one has a minus 6. And now let's plug in our values. So we're going to plug in 5.9 for the x and 4.05 for the y. And that's basically it. We just have to simplify now. Okay, so we get 10 plus 3/5 times 5.9 minus 6 is negative 0.1, negative 0.1. And then we get plus 12/5 times, this one's going to be 0.05. Okay, but we can rewrite these decimals as fractions. So this is equal to negative 1/10, and this is equal to 5/100. So continuing to simplify, we get 10 plus, so 3/5 times negative 1/10, that's actually going to be negative 3/50. And then 12/5 times 5/100, we can cancel the 5s. And if I were to divide the top and the bottom by 2, I'll get a common denominator. So I'll end up getting plus 6/50 if I do that. And so we get 10, and then negative 3/50 plus 6/50, that's plus 3/50, which is 10 plus 0.06 as a decimal, which is adding these 10.06. That's our approximation right there. So notice that we were able to get this approximation without a calculator at all. It is a lot easier in general to plug into a linear function like we have here than it is to try to plug into this complicated square root of x squared plus y cubed function. Okay, how close is this? Using a calculator, 5.9 squared plus 4.05 cubed, if we square root that whole thing, this is approximately equal to 10.06181519. That's going to 8 decimal places. But that's pretty close to what we got. We got 10.06, which is very close. Okay, and part of the reason why it's very close is the points that we were plugging in, 5.9 and 4.05, they were super close. They were super close to our known values that we were basing our approximation off of, where x equals 6 and y equals 4. Typically, that's going to be the case. The closer our point is, our approximation point, to this known point that we base the approximation off of, the closer our approximation will be. So in the next video, we will talk about what are called differentials. And differentials are going to be a way for us to perform some error analysis.